When you put salt on the front walk to melt the ice, you see melting around the salt grains as shown in this photo. However, something surprising happens to the temperature. The snow gets colder. Melting around the salt grains is key to understanding the cooling, which I will explain in terms of the latent heat of melting. Towards the end of this video, I'll touch on two ways that the latent heat of melting contributes to avalanche formation. But first, let's start by measuring the temperature of the snow before and after we add salt to see if we can measure the cooling. Here is a bowl of slightly moist, coarse-grained snow that I brought in from outside. This handheld infrared thermometer measures the temperature of the snow surface. The snow is slightly moist, and accordingly, the surface temperature is at 0 degrees Celsius. Well, at least within the accuracy of the infrared thermometer, which is 2 degrees. Now let's add some table salt, that is, sodium chloride. Other salts, such as calcium chloride, are also used for melting ice on roads and sidewalks. Note that I have added more salt to the upper right side of the bowl. The infrared thermometer shows the temperature dropping, especially where more salt was added. The area where I added the most salt is the coldest. Here is an infrared image of the snow surface and bowl. It was taken from the side opposite the video camera, so I'll rotate the image so it is oriented the same way as in the video. The yellowish-green color indicates where the snow surface is still at the melting point, 0 degrees Celsius. The dark blue areas are where the snow surface is much colder, down to about minus 20 degrees. The area with more salt is here, and it is colder than the unsalted areas. Where the most salt was sprinkled, we can see pits where the grains have melted down into the snow. This is similar to the melting around the salt grains in this photo from the start of the video. Looking more closely at the thermal image, we can see cooling of the snow surface around the salt grains or clusters of salt grains. So the salt grains have caused some melting and cooling of the snow around the salt grains. Cooling associated with melting is a head scratcher and needs an explanation. Here's a drawing of a salt grain surrounded by snow or ice. We saw melting around the individual salt grains, so there is concentrated salt water around the grain, which I've shown in blue. Where the salt or concentrated salt water touches the snow, shown in yellow, the snow melts. The latent heat for melting the snow around the grains came partly from the air and mostly from the snow. So heat from the snow flowed towards the saltwater boundary, cooling the snow. However, concentrated salt water freezes at minus 21, so the snow cannot be cooled below minus 21 degrees. Basically, the heat of melting is a large quantity, so only a small amount of melting next to the grains is enough to cool the snow around the sprinkled salt. Let's look at the latent heat graphically. Here is what happens to a kilogram of ice when heat is added to it. This graph starts at minus 100 degrees Celsius. As heat is added along this axis, the ice warms up along this slope, then it plateaus at 0 degrees Celsius while latent heat is absorbed by the kilogram of ice that is melting. A kilogram of ice or snow absorbs 330 kilojoules of latent heat in this melting process, more than is required to warm the ice from minus 100 degrees to the melting point. I find the latent heat of melting snow by itself fascinating. However, if you're wondering what it has to do with avalanches, here are two examples. First example. When dry snow falls on a wet layer, the latent heat in the wet layer makes it slow to freeze. So part of the wet layer stays at 0 degrees Celsius while the wet layer is freezing. When the surface of the dry layer is cooled, typically by radiant cooling to a clear sky, the temperature gradient in the dry layer increases, especially at the bottom of the layer. A weak layer of facets on a crust can release hard-to-forecast avalanches, sometimes for months. In November 1996, this process of dry-on-wet faceting created a weak layer throughout much of Western Canada. This photo shows one of the many avalanches that released on the facet-crust combination during the winter. You can search the web for Vimeo facets crust for a video with more on dry-on-wet faceting and the winter of large avalanches that released on a layer of facets. Example 2. The very start of rain on fresh dry snow can trigger slab avalanches. Because of latent heat, few millimeters of rain contains a lot more heat than a few centimeters of dry snowfall. And rapidly adding heat to the snowpack can lead to avalanches. Here's a paper by Conway and Raymond on the subject. Unfortunately, I don't have a photo of an avalanche that released at the start of rain on fresh dry snow, so this photo will have to do. In it, the slab avalanche released on a buried surface hoar layer after sustained rain. The concept that connects these examples of avalanche formation with sprinkled salt on snow is the surprisingly large amount of heat required to melt snow, that is, the latent heat of melting. I welcome your comments on any of these videos.